Last report.
Okay. All right. So I want to make sure everybody's kind of cool with what's going to happen with this lab, and there's going to be three main parts of the lab. One is on friction, and that's brought to you by the equation that mu equals force friction over force normal. This is like an absolute value. So on your sheet, you're going to calculate the coefficient of friction between this block of wood and the wood back there on the countertops. So you're going to use this scale. You guys are the first ones to ever use these digital scales. It's the first time I've ever had to. Woo, yeah, okay. So otherwise I had these old mechanical spring ones. You guys are high tech, right? So the main thing is that once they're turned on, that you have to re-zero them in the direction that you're going to pull them. Okay? So if you're going to pull this thing horizontally, put it down. If it's not reading zero, just hit that zero button and it'll read it out. So if you're going to pull it for static friction, increase the force until it just begins to move, and then you're going to pull it at a constant velocity and use that for kinetic. Now, those surfaces back there have some variance just because those surfaces have been around since like 1996, okay? So they've been around a while. So make sure that you kind of use the same area each time. Okay, you can kind of look at it and kind of look at that. So you're going to do different types of material, wood on wood, aluminum, sandpaper, and cotton. Okay? So that's going to be that. Hopefully you all have watched that video already because I don't have time to go through everything again because we need to get a bunch of data collected today. So then the next part, you're going to begin to stack weights on top of it and do that same thing. You're going to add weights, pull it, add weights, pull it, add weights, pull it. You're going to draw a graph with force friction and force normal. You're going to find the slope of that line. Pay attention to the fact that I want you to draw a line of best fit. I want to see the points that you circle. I want to see how you found that slope. Okay? And here's the biggest thing that you have to remember. The only reason that you have to apply a force to keep something moving is because of friction. If you eliminate the frictional force, you don't have to keep applying a force to keep it moving. So like if I take the hockey puck, right, and I turn that on, and I give that a slide, okay, that's just going to keep going and going and going because there's no frictional force to make it stop. So if you have to keep pulling that block, the only reason that you have to keep applying that force is because there's friction. You eliminate friction, you eliminate the force needed. Inertia, which is basically the tendency of an object to maintain a constant speed, is what's going to keep it going. Okay. So you got a bunch of questions to answer to that. You're going to have to draw a free body diagram. It's going to look like this. Make sure you label your gravitational force, your normal, your FAP, and your force, or FOP, opposing force, or force friction, whatever you want to call it. Okay? FAP, FOP, FG, okay? Make sure you have those. Make sure I see your scale, okay? Make sure that I see your scale. You're going to draw this with a ruler. Then you're going to draw another one that's going to look like this, and you're going to draw it, hold on. You're going to draw that one tip to tail, FG, FAP, normal, okay? Force friction or force opposing, you should end up back at the origin. Okay? That's the main part of that. Then you got a bunch of questions to answer on that. So the other part, let's go back. Is anybody zoomed in?
No.
Then let's not go back.
Do you want me to end it then?
Nah, keep it going just in case, but nah, go ahead and end it.
Yeah.
Okay. All right, so we do need to bring this though. Can you be in charge of that?
Yep.
Okay, thank you. All right, so Ron, right here. Yep.
I accidentally just took your job.
Okay. So the second station, and I've got 3 of these set up. Okay, and I want you all to work in like groups of like, I want 3 groups, as many as you are. Okay, I want like 3 groups. So this is a table, and we use it to study forces, and we call it a force table. Not the most clever marketing name in the world, but the name gets across. So what you're going to do is that you can manipulate 2 different things. You can manipulate the force that's pulling down and creating tension in the string, and you can change the angle. Okay? So what you want to do is to set up a situation where this center ring is centered on this peg where it isn't like hitting the side of it. So you can adjust the weights, you can adjust the angles until you get this ring where it's centered. Now, I don't want 3 identical weights hanging from each side. That isn't the point of the lab. Okay, you're gaming the system. I want 3 different weights. Now, you want to keep one of these angles at 0 degrees. Okay? Keep it simple. Make one at 0. We're going to call that vector A. Then what you want to do is go, so if you're like this, let me turn this a little bit. Okay? So here's going to be 0 degrees. So then you're going to measure counterclockwise, and this is already marked in the top of it. You don't have to have a protractor. The grid that's already marked off. So then this one would be like 89 degrees, and then this one over here would be 132. So those would be my angles. So A is going to be at 0, then you're going to have B, then you're going to have C. Once you get it in equilibrium, then you're going to take off the weights, okay, and then you're going to add up the total amount that you have suspended. These are going to be in grams. It's a simple conversion. Convert them into kilograms, divide by 1,000, multiply by 9.8 meters per second squared. So over here on page 2, okay, where you can have vectors A, B, and C. The first angle is 0. You're going to have that mass, whatever that total mass is hanging down. And then your FG is just going to be take that mass in kilograms multiplied by 9.8 meters per second squared. Don't make that negative, okay? Don't make these weights negative. You're going to define the system based upon these angles, okay? So, once you get that done, you're going to have these numbers. Here's what I want you to think through. This is like a 3-way tug of war. So you have vector A, vector B going like this, and then you have vector C. So if you were to add these tip to tail, here's vector A, here's B, and then you'd have C going that way, you should end up back at the origin. Okay, that's one way to think about it. The other way is that if you drew vector A, and then you took vector B out this way, and that's the only thing you had was those 2. The resultant would be going out in this direction. So what this vector over here is doing is it's balancing out the effect of these 2. This one is balancing out the effect of these 2. A is balancing out the effect of those. So what you should see is that these are, what each one is doing is balancing out the resultant of the other 2. Okay? So, you got some diagrams to do on that. So, once you get that done, okay, then using the force table, here's your data table. You're going to draw them tip to tail. Why didn't the ring accelerate? There you go. That's going to be the relatively simple one. So, let me change this so you all have to get it back into equilibrium, and you all can figure it out there. Okay. All right. Now, here's what's going to be the most complicated one. Watch out. Watch out, watch out, watch out. Okay. So, what you're going to do is that you need to find the weight of this cart. You have your handy-dandy Newton scale, hang it up, get the weight of the cart. Just hook it in, suspend it like that, that's the weight of the cart. So if you know the weight of the cart, how can you find the mass of the cart? Divided by 9.8 meters per second squared. So to get the mass of the cart, take what it weighs, divide that by 9.8 meters per second squared, boom, there's your mass. So you need a cute little 10-gram mass, you get 20-gram mass, and you need a 500 gram mass. So what we're going to do is we're going to have this up here. We're going to put that cute little 10 gram mass on the end, okay? We're going to push this back like so. And what you want this thing to do, you want this thing to travel 50 centimeters. Okay, so I don't care which marks you pick, but you want it to travel 50 centimeters. So what you're going to do is you're going to have it like this, okay? So maybe you're going to start at like 100 centimeters, okay? So you're going to have that front edge at 100. So you're going to have it like this, and you're going to let go, and then you're going to stop it when the front edge crosses the 50 centimeter mark, okay? I tell you to go from 15 to 65, it doesn't matter, just as long as you travel 50 centimeters. So, we're going to get clever here, okay? So, pretend that this thing isn't even here, okay? Let's just focus on that 10 gram mass. 10 grams, does anybody have a calculator? Because y'all are horrible at doing mental math. So, but go grab a calculator. So, forget that it's attached to anything. 10 grams is how many kilograms? What are you going to do?
Divide by 1,000.
Divide by 1,000. So take 10 and divide it by 1,000. And you get 0.0001. Okay? Now, I'm going to multiply that by 9.8 meters per second squared to figure out how much that weighs. So multiply that number, divide by 1,000, and multiply by 9.8. What do you get?
0.098.
0.098. So what's happening is that gravity is pulling down on this force with that value of 0.098 newtons. So when I suspend this thing from the edge of the table like this, okay? So you've got a downward pull of 0.098 newtons. The tension on the string is acting upwards with a balancing force of 0.098 newtons. The system is in equilibrium. Now, here's the most important thing. If I just cut the string, okay, if I just cut it, boom, cut it. The only force acting on that is 0.098 newtons. I divide that by the mass, I would get an acceleration of 9.8 meters per second squared. Okay? So here's what's going to happen. When I let go of this thing, okay, and here's the most important thing to understand. When I let go of this, the force acting on this system is caused by gravity pulling down on this little weight down here, which is going to have a value of 0.098 newtons. Now, but it's just not going to accelerate the 10 grams. It's also going to accelerate this whole system up here. So that 0.098 newtons is going to accelerate the 10 grams, but it's also going to accelerate the 20 gram. It's going to accelerate the 500 gram, and it's going to accelerate the cart itself. So when you look at force net equals mass times acceleration, you're going to hear me say this again and again and again and again and again. The mass has to be the combined mass of the entire system. It isn't just the mass that's on the end of the string. Okay? It's also the mass that's up here on the cart itself, the 20 and the 500. So what you're going to do is you're going to run this like 5 times. Okay? You're here, let go, boom, let it fall to 50 centimeters. You're going to do that 5 times to find an average time. Now, when you get done with that, you're going to swap out the 10 grams for the 20 grams. Now, I'm going to do this, but here's what's important. Now I want to put that 10 gram mass back up there. Why do you think I put that 10 gram mass up there, Mr. Bird?
So that between both trials you have the same net amount of weight in the system?
You're off by one word.
Mass.
Mass. Okay? That way the combined mass of the system is going to stay the same. So we're going to look at net force equals mass times acceleration. We're going to keep the same mass. Okay? We're going to change the distribution of it, but it's still going to be the same mass that's going to get accelerated. So we're going to be here. Now, what do you think is going to happen to the acceleration of the system when I put that 20 gram mass out there? Mr. Bird?
Since it's 20 gram mass, then force equals mass times acceleration. We have more mass, same acceleration, more force, so it'll move a little faster.
Yeah. So now we're going to apply more force on the end of this thing, right? Because gravity is going to pull down with 20 grams. So, go to take 20 grams, divide that by 1,000, multiply that by 9.8 meters per second squared.
0.196.
Okay. So now we have 0.196 newtons of force acting on here. So now when I let go of it, we're going to get a much bigger acceleration. Because now we have twice the force acting on the same mass. We should get twice the acceleration. Okay. So you're going to do that trial 5 times. Got it? Good? Okay. Back we go. So I need to do some more writing up there on the board, and then I'm going to turn you loose. No. No. Bad things going to happen. Yeah.
I felt like
Okay.
Gotta make sure my head's not gonna be in it when I sit down.
Okay. So here on page 3. Okay. So up here, you're going to run the 5 trials. Make sure that when, here's the one thing you have to watch, is make sure that that weight that's falling is above the ground when it passes like that 50 centimeter mark. In other words, don't have that hit before you've traveled the 50 centimeters. That's the only thing that you really have to watch out for. So your net force, like on that first trial, Bodie took 10 grams, he divided it by 1,000, and then he multiplied that by G, and you got what, 0.098?
yes.
Okay. So, on that first trial, you had that cute little 10 gram mass hanging from the end. So, the force available is 0.098 newtons. That's the force available to drag this thing down. Okay? Cart's up here, so that's the force that's going to make this whole thing move. Okay? So to get your theoretical acceleration, you're going to take 0.098 newtons, and we're going to assume that this is a frictionless surface, and we're going to divide that by the total mass of the system. So your total mass of the system is going to be, you're going to have to find the mass of the cart, add 10 grams to it, add 20 grams to it, and add the 500. So the total mass is going to be 10 plus 20 plus 500 plus what you get for the mass of the cart. Okay? So this is going to be your theoretical acceleration. 0.098 divided by the total mass of the system. Now, to get your experimental acceleration, we're going to see how close these two numbers jive up. What you're going to do there is you're going to use distance equals 1/2 at squared plus v naught time. We're clever, right? We let the initial velocity be 0 because we started this thing from rest. Oh, guess what? We don't have to worry about that part of it. Okay, so that whole thing goes away. You're going to know how far it went. It went 50 centimeters. Make sure that's in meters. Oh, it went 1/2 meter. Oh, okay. You know the time. You're only going to do one calculation of this with the average time. So you're going to know your time. So the only thing you don't know is the acceleration. So you're going to go 2d divided by t squared is going to equal your acceleration. So that's going to get you your experimental acceleration. Okay? So your theoretical is going to be the weight of what's ever hanging down divided by the total mass. Okay? Your experimental is going to be 2d over t squared. So Then you got a bunch of questions to answer on that. And let me give you a hint on number 10. I'm going to give you a bunch of statements, and I'm going to ask you if they're true or false. Let me give you a hint. Every one of them is false. The whole key is to explaining why they are false. So on number 10, there is not a true statement on any of them. Okay? On number 12, when it asks for like an action-reaction pair, that's where something is going to act on something and something is going to act with an equal and opposite force. So like the classic example, if I push down on the table, then I'm pushing down on the table is providing an upward force acting on me. Gravity is pulling down on the weight, okay? So the earth is pulling down on the weight is pulling back up on the earth. Gravity is pulling down on the string is pulling back up on the weight. There's a whole bunch of different things that you could have on number 12. A contact force, by its nature, is something, guess what, that requires contact. A long-range force would be something that acts without contact. Let me give you a hint. Gravity. Just so. Okay, I am done. So, there's a video out there that explains assignment 4.1. That's what you all need to worry about tomorrow. So this lab and assignment 4.1 are going to be due on Monday. Okay? So, I'm done. Go collect data.
You want to start on the same? Start on one.
So, 3 groups.
How many people are in this class?
12, I think?
There are 10.
Arithmetic?
Just a little bit after. Are you gonna stop at 2, 1? Oh, hold on. A little too slow. No, I didn't start it. Okay.
No, I mean, it helps. If you put it both in
3,
parentheses, and since you know you have
2,
constant,
1.
that never touch that voice, you use the first parentheses.
Stop.
That's what I do when I'm, that's what I do when I'm in a test.
Hey, we got another 2.82.
This is cotton, Josh.
Okay.
This is cotton, Josh.
And the average is 2.7.
This one's good. This one's gonna be.
Okay, now we have enough weight.
What is this?
It's cotton.
Oh,
2.23.
That's what.
We can take a guess. I saw like 1.6.
I saw 1.8.
I saw 1.8. Oh,
It's the vegetation.
it's 2.18. That's like the most rounded I got out of the ones I saw. 2.18. I remember to put my units for this. All right, and then
20, each of those is 20 grams.
But the bottom one's different. You can just take them off.
We did it, but now
Okay.
we have to take it apart to get the
10.
mass.
Okay.
Because we didn't read it before, so,
Yeah.
yeah.
Okay.